Hello and welcome. Today I'm going to be sharing a paper I discovered entitled Tarzan, a peer-to-peer anonymizing network layer. If you're curious about online privacy, decentralized systems, or how to keep your communication secure and untraceable, you'll find this topic quite interesting. Tarzan tackles the challenge of anonymous communication by disturbing trust across a wide network of volunteer nodes. So rather than relying on one big central service, it uses peer-to-peer approach and layered encryption, reminiscent of a classic kind of Chumain mixes. If you've heard of them before, I'll go further into detail later in this recording about what Chumain mixes are. In this presentation, I'll introduce you to Tarzan main ideas, why anonymity matters at the IP layer, how peer discovery and domain-based selection works, and how covered traffic can disguise who's actually sending data. I won't deep dive here at the start, but I promise I'll walk you through and have a solid understanding how Tarzan architects solve these complex security and networking issues. So, jumping into some motivation here, why does anonymity matter? So, anonymity on the internet matters because it protects our basic right to privacy, whether we're sending personal messages or doing research or simply browsing. Unfortunately, a lot of existing anonymity solutions rely on centralized proxies or small clusters of specialized relays, and this is a huge vulnerability. If these critical points are compromised or attacks, privacy can be lost. In reality, threats come from multiple directions. Some nodes within the network might be outright malicious, spying on tampering user traffic. Meanwhile, powerful global observers like major ISPs or government agencies can see vast portions of the internet and analyze communication patterns. To truly safeguard privacy, anonymity systems must be decentralized, robust, and easy to scale. That's the motivation behind architectures like Tarzan, which we will jump into next in the next coming slides. Here is a high-level visual that shows how Tarzan's network might look in practice, just for visualization for the viewers. Each shape and color represents different roles. White squares are for honest routers, black squares are for malicious routers, and circles are normal nodes, and each shaded circles for spoofed or adversarial ones. You can see these circles for normal nodes and shaded circles for spoofed and adversarial ones. And you can see these nodes are spread across various subnets or LANs. The border gateways connecting them through the larger internet clouds. The dotted outlines mark corrupted domains, subnets that have fallen under adversarial control. The key takeaway here is that Tarzan treats every node as a potential relay or source, but also plans for the possibility that some domains or nodes are compromised. On the next slide, we'll go deeper into how Tarzan's design handles these mixtures of honest and malicious nodes to preserve anonymity. As stated previously, Tarzan is built on a peer-to-peer architecture, meaning that no single authority or small controls traffic flow. Every participant can relay packets, making it more resilient. It achieves IP transparency by operating at the network layer, so you can keep using your favorite apps without any code changes. At its core, Tarzan uses layered encryption. So in other words, each message is wrapped into multiple cryptographic layers, and every relay in the chain peels off just one, kind of like an onion. There's actually a similar networking protocol for security called Onion. This setup combined with multi-hop tunnels ensures no relay knows both the sender and the recipient. Meanwhile, Tarzan's domain-aware selection ensures that nodes are drawn from different IP subnets, preventing adversaries from overwhelming a path with many compromised nodes in one domain. There's also a covered traffic mechanism. So nodes maintain steady dummy traffic so that transmissions aren't distinguishable from the noise for like a observer. And finally, PNAT or pseudonymous NAT, which is network address translation, which bridges Tarzan traffic to the regular internet without exposing the true user's IP, protecting identity at an edge or a possible edge case. So now that you have a bit of an overview and a background of what Tarzan is and how it works, we can jump into the problem statement of what Tarzan is specifically trying to solve. So Tarzan envisions a large internet-wide pool of volunteer nodes, potentially in the thousands, that relay one another's traffic. This design encounters two key threats, which is malicious nodes that could go logged and tamper with data, and powerful eavesdroppers that monitor entire backbones or large network segments. Unlike some older systems that focus on small, fixed sets of relays or underestimate how easily nodes can be compromised, Tarzan's approach ensures both scalability and resilience. So, in other words, it's specifically built to handle real world challenges of massive surveillance and determined attackers. On this slide, you can see how Tarzan delivers application independence by working at the IP level, as the diagram explains down below. The client application sends packets as usual, and the operating system diverts them to Tarzan's initiator. From there, each packet is wrapped in multiple encryption layers and forwarded through a series of relays before hitting the PNAT, as described previously, which finally sends the traffic to the public internet. Because Tarzan intercepts packets below application layer, as said previously, no code or application code is really need to be changed. The design also strengthens sender and recipient anonymity. Every relay only knows the previous and the next hop, not the entire source destination pair. Meanwhile, Tarzan's decentralized architecture avoids single points of failure, ensuring higher fault tolerance if an individual relay goes down, and the system adds only minimal overhead. It is still performant enough for interactive uses like web browsing or even SSH sessions. And lastly, all these elements work together to resist a global eavesdroppers, making it extremely difficult for any adversary who might see vast portions of the network traffic to pinpoint who's talking to who. Here, each donut chart represents a different threat dimension. First, a portion of nodes are malicious. In any open system, that risk is unavoidable. Next, while most IP prefixes remain uncompromised, a significant fraction belongs to attackers. Tarzan concepts of domains, whether it's 16 or 24 prefixes, controlled by a single real-world identity, is crucial because it's an adversary who compromises a gateway or router for that domain can spawn multiple malicious Tarzan nodes. By selecting relays from distinct domains, Tarzan prevents one compromised subnet from dominating an entire path. The third donut underscores the global eavesdropper threat. A large-scale surveillance can observe massive swaths of traffic, so Tarzan employs cover traffic and multi-hop routes to confound correlation. And lastly, there's always a possibility of collusion among several malicious domains, which Tarzan mitigates by randomly scattering relays across the network, reducing the chance that an attacker can piece together a complete communication path. So before jumping into very specific protocols or things that Tarzan implements, we're going to go over some basic assumptions that it makes. So Tarzan assumes a large-scale eavesdropping can happen. So like very small P2P networks, that may not happen just due to the size of the node network. But so it's built with constant rate cover traffic to hide real send patterns. Also, because the network is open to anyone, there's no strict admission control, so no centralized certificate authority, much like how they had regular networks. Instead, Tarzan prevents attackers from dominating the relay pool by randomly selecting nodes from previous domains, as previously mentioned. This combination of cover traffic and domain-aware randomization addresses both the risk of global snooping and the possibility of malicious nodes trying to overwhelm the network. So here are the core components that makes Tarzan work. First, we have tunnels, which are basically multi-hop paths taken across volunteer nodes. The PNAT, or pseudonymous NAT, sits at the very end of the chain and bridges to the regular internet, as mentioned previously. Next, Tarzan relies on layered Chumayan encryption, so every hop along the tunnel either removes or adds a layer of encryption, depending on the direction of travel. Forward removing a layer, and then reverse would be adding a layer. Finally, we have flow tags in MAC, which provide an efficient way to label and verify packets as they move through each relay, ensuring no single hop can peek or modify at other parts of the tunnel. In this following slides, I'll break down each of these pieces so they all fit together and make more sense in the following slides. So the first core component we'll be getting into is the tunnels component. So Tarzan sets up tunnels in an iterative fashion. The iterator picks volunteer nodes one by one and sends a secure established request and waits for a corresponding established response. Once the tunnel is fully formed, the last hop becomes a PNAT, so bridging our traffic to the wider internet. When it comes to packet forwarding, Tarzan's IP forwarder intercepts traffic on the client side, NATs, it to a private address, and then wraps each packet in multiple layers of encryption. On the other end, the PNAT performs a reverse NAT, representing its own IP to the actual destination, so the true source remains hidden. Within Tarzan's packet relay mechanism, all data is encapsulated in UDP, which tagged with sequence numbers, flow identifiers, and per hop MACs. This setup lets each relay node quickly verify integrity and route the packet without learning too much about the contents or final destination. If any packet fails, an MAC or sequence check is discarded to prevent any replay or corruption. And finally, feature or failure handling keeps the tunnel robust. The initiator pings its relays, and if a node isn't responding, it's swapped out for a new relay. Even if the PNAT fails, Tarzan can assign a different exit node, so ongoing connections aren't completely lost. Together, these protocols ensure a stable, secure, and anonymous path. Tarzan relies on peer discovery so that every node gains awareness of the entire network. It uses gossip protocol, where nodes continuously exchange information about who else is out there. New addresses initially land in an unvalidated pool, and once a node challenges them and sees a correct response, they move into a validated list or pool. This prevents spoofing or fake addresses. Next, Tarzan cover traffic and mimic links help to ensure that global eavesdroppers can't trick who's actually sending data. Nodes establish a handful of bidirectional mimic connections, each running at a steady rate. Over short time slices, they intermix dummy packets with the real data to obscure traffic patterns. So if someone's listening, they see a uniform flow rather than spikes to figure out abnormalities to ensure security. And then finally, domain-aware peer selection is how Tarzan prevents single compromised subnet from dominating a tunnel. Rather than picking random IPs from a big pool, the system first picks a 16 domain and then narrows it to a 24. And then after finally selecting a specific IP within that subnet, this process spreads out the potential relays, limiting an adversary's ability to insert many malicious nodes from the same domain. When we compare Tarzan to systems like onion routing or crowds, we see that a malicious first or last hop can often discover the sender or the receiver. Tarzan's peer-to-peer homogeneity solves some of that by not labeling any node as strictly entry or exit. They're all just relays, so an attacker can't easily pinpoint who started a connection. Two major threat models came up, a static adversary that already controls specific nodes or entire domains, and a time-bounded adversary who compromises targets gradually. Tarzan addresses both by treating IP prefixes as domains rather than picking random IPs from global pool. This domain-based analysis makes it far harder for attackers to send multiple malicious hops on a single path. Meanwhile, cover traffic keeps traffic rates uniform. Each node ensures its inbound rate is roughly equal to its outbound rate, preventing an observer from spotting the actual source of data. Tarzan's mimic connections also inject dummy traffic to hide spikes in usage. And lastly, exit point attacks like replay or tagging are blocked by sequence numbers and MAC checks, while reordering batches of packets adds an extra layer of confusion for eavesdroppers trying to do timing analysis or other forms of peeking and obscuring data. When we look at Tarzan's performance, one of the standout points is that the packet forwarding overhead stays quite low. In a local LAN environment, each hop contributes under a millisecond of extra encryption and routing delay. Notably, notably, a single Tarzan relay can handle enough throughput to saturate a T1 line, which is an older but still relevant dedicated circuit that provides roughly 1.5 megabits per second of bandwidth. Tunnel setup does come with some overhead due to mostly having iterative key exchanges. In practice, forming a multi-hop path might add around 20 milliseconds per hop, which is perfectly acceptable for most interactive uses. However, the cover traffic required to hide real transmission patterns can feel wasteful if you're sending only small amounts of data. Tarzan addresses this by letting you tune the dummy traffic rate so you can get the right mix of privacy and efficiency. And finally, peer discovery is handled through a gossip protocol with ON connection complexity, which the authors seem to argue is reasonable, even if the network grows at a few thousand nodes. So this ensures that each Tarzan node eventually learns about all the others, preserving both performance and strong anonymity. We have now reached the end of the video, so thank you for listening. If you have any questions, don't hesitate to ask. Um, and I hope you learned something. Thanks for watching.